Finally, we come to the fluid dynamics. In this one, we will study two important equations. One is the law of conservation of mass, second is the law of conservation of energy. That is the Bernoulli equation and the law of conservation of mass. That is a continuity equation. So we have a mass flow rate is given by m dot, volumetric flow rate is equal to q, meter cube per second. Mean velocity is given as u bar, which is meter per second. Volumetric flow rate is simply the q, which is given as a product of area multiplied by velocity. So whenever we write area multiplied by velocity, in that case this velocity is the average velocity and the area and the velocity, they are always perpendicular to each other. Mass flow rate can be computed using the discharge as a product of rho multiplied by q. So mass flow rate is given as density multiplied by area multiplied by velocity. So whenever we say area and the velocity are perpendicular and the distribution of a velocity is constant here over the entire section, that is called as the average velocity. But normally, due to the viscous nature of the fluid, the distribution is not the average velocity, but rather is a parabolic form of distribution. So whenever we have a parabolic form of distribution, then the idea is to consider here a elemental ring where the velocities remain constant and that equal to u, and we will consider here one elemental strip which has the area equal to dA, which is for in the case of circular pipe you have to take this ring equal to 2 pi r into dr, and in the case of the flat plate we have to take this area as a width multiplied by dy. So using this elemental area multiplied by u, you can calculate dq. So we have dq equal to u multiplied by dA. And finally, to calculate the total discharge, you have to integrate this equation, and you have to integrate this as integral of u multiplied by dA. In the case of pipe you take 2 pi r dr, and in the case of flat plate you take b into dy. But before this we must know how the distribution of u with respect to r and with respect to y. Finally, you equate this total discharge with area multiplied by u average, and from this one we can calculate the average velocity, which is given as u bar equal to 1 by a integral of u dA. That is, the u bar is nothing but area weighted average of the velocity. So here I demonstrate here how to calculate the average velocity in the case of pipe flow, where the velocity v is a function of r, and at any radius r your velocity is given as u max into 1 minus r square divided by r square, where u max is the center line velocity, that is r equal to 0. And using this definition of u, we'll consider here one elemental ring of area equal to 2 pi r dr, and then we'll use the definition, that is 1 by a integral of u dA. So we have 1 by a, u is replaced by u max into 1 minus r square by capital R square multiplied by area is 2 pi r dr. We have a limit is from 0 to capital R. Step by step solve this, and whenever we have this relation, it is proved here that we have average velocity equal to half of maximum. The mean will lie exactly half of the height of the parabola, and the height of the parabola here is u max, so this value is present here, the value of u average. But if you are given here rectangular duct of a cross section is t multiplied by w and the L is the length, and we have given the variation is something in this profile, that is a function of y. So this time we will consider here one elemental strip at distance equal to y, thickness equal to dy, correspondingly we have velocity equal to u. So this is the perpendicular section here, is like this one. So using the concept again, the average velocity will be equal to u multiplied by elemental area, that is w into dy divided by total area. Solve this equation, we will get the average velocity. This time I have not taken the distribution, otherwise we can develop the equation for this, for the rectangular channel. Now the rectangular channel concept can also be applied to find out the discharge over a flat plate in the case of boundary layer. So as we know that boundary layer, this one is called as the leading edge, this one is called as the trailing edge, and we have a length equal to L. Initially we have a laminar flow and then we have a turbulent flow. The distribution in the laminar is different, and in the case of turbulent will be different. So if we know this distribution here and we want to calculate how much mass will move from the section AB, so you have to consider one rectangular elemental area of height equal to dy and the width equal to w, and assume that the velocity through this is remain constant equal to u. So we have area equal to w multiplied by dy, and The velocity is expressed as u upon u infinity equal to 2 by 3 y by delta minus 1 by 2 y by delta q. Once we know this equation, then we can calculate here what is the discharge through the section A to B whose height equal to delta. The volumetric flow rate through AB is given as integral of del q, which is simply equal to the velocity u multiplied by dA. And here we have to write down this u in this form, and dA you have to take as width, which is equal to w multiplied by dy. So you just substitute here u as a u infinity multiplied by this bracket, and we have w into dy. And the total height here is from 0 to delta, so limit is from 0 to delta. Solve this integral step by step. Finally we'll get here the discharge through this one is 5 by 24 u infinity into rho multiplied by w. And whenever we know the discharge, we can calculate mass flow rate just by multiplying rho. So we have a mass flow rate to the section AB will be equal to 5 by 24 rho multiplied by u infinity multiplied by delta multiplied by w. Out of this, rho u infinity and w is remain constant. So only delta matters here. As the delta will go on changing, the mass flow rate will also go on changing here. Remember here some mass is entering from the top side also. So suppose we have given here two sections, one section is AB and one section is CD, and he is asked you that how much mass enter from the section BD. So just now we have solved for AB section, that answer is 5 by 24 rho multiplied by u infinity multiplied by w, and it depends upon the height of boundary layer thickness that equal to delta 1. Similarly we can calculate here how much mass is leaving from the section CD. So this mass flow rate is m dot CD, this mass flow rate is m dot AB. So almost you have to copy down is 5 by 24 rho into infinity into w. This time delta 2 matters here. So naturally this mass is more because more value of delta 2. This mass flow rate is less. Apply the law of conservation of mass. So we have two mass inlet and one outlet. So we have m dot AB plus m dot BD must equal to m dot CD. So how much mass will enter from this side, which is open to the atmosphere, that we can calculate is m dot BD equal to m dot CD minus m dot AB. So for given distribution, this answer will be equal to 5 by 24 rho into u infinity into w into delta 2 minus delta 1. The another equation important for us in a fluid dynamics is the Bernoulli equation, which is basically derived from Euler equation. So we'll consider here one streamline having a velocity equal to v, and we'll consider one element of length equal to ds. The weight is acting in a downward direction. So right now we are defining here weight per unit mass. So the weight will be equal to, per unit mass will be equal to g. So we'll resolve this g component, one parallel and one perpendicular. So this component is parallel to the streamline here, that equal to minus g times sine theta. And the acceleration is along this direction is given as dv by dt, which can be written as dv by ds into ds by dt. ds by dt is same as the velocity. So acceleration is given as simply v multiplied by dv by ds. So this time we have net force acting along this direction will be balanced by the inertia, that equal to m into a force. So we have net force acting is minus g sine theta. The another force is acting is pressure force, which is equal to 1 by rho del p by del s equal to v times dv by ds. Solve this equation and multiply by ds. We can generate the Euler equation, which is dp by rho plus v dv plus g dz equal to 0. That is change in pressure divided by rho plus v into dv plus g dz is always equal to 0 along the streamline. If we integrate the Euler equation between the two sections, it will generate the Bernoulli equation. And the Bernoulli equation is derived assuming that the flow is steady, incompressible and the frictionless, with no external work done and the heat transfer. And it is purely applicable along the streamline. So integration of this one is dp by rho plus we have integral v dv plus g dz. Some assumptions are in the Bernoulli equation is that there are no shear forces, that the fluid is ideal and non-viscous, the fluid is incompressible, the body forces are only due to the gravity, the flow is steady, and the equation is applicable only along the streamline. So if we integrate this, we'll get p by rho plus v square by 2 plus gz equal to c. That is the total energy per unit mass of a flowing fluid is always equal to constant. That is the statement of Bernoulli. Here p by rho g is called as pressure head, V square by twice g is called as velocity head, z is called as potential head. Since each term here are head, E is called as total head and is basically meters of flowing fluid. If we multiply each and every term by rho g here, this equation can be written as P plus 1 by 2 rho V square plus rho g z equal to another constant equal to C1. This time P is called as static pressure, 1 by 2 times rho V square is called as dynamic pressure. And we are familiar with rho gz, that is called as hydrostatic pressure. The sum of the pressure, that is the static pressure, and the hydrostatic pressure is given another name, that is called as piezometric pressure. Here P by rho is called as the flow energy or is called as work. V square by 2g is called as kinetic energy and gz is called as potential energy. But all these energy are per unit mass. So Bernoulli equation gives you the idea of the total energy, but energy is expressed as per unit mass. This is shown here. The kinetic energy of the total mass is 1 by 2 mv square, per unit mass is m, so we get 1 by 2 v square. So we have a unit equal to energy per unit mass. So each and every quantity this time is the energy per unit mass, and if we divide it by g here, then it becomes energy per unit weight, which is P by rho g plus v square by 2g, and g cancel is z. Even the Bernoulli equation applicable for the ideal fluid where the losses are 0, but we can very well modify the Bernoulli equation. Suppose the direction of fluid is given from 1 to 2 and we have a property is P1 Z1, P2 V2 Z2, and we have a losses taking place because of the friction. In that case, since the direction is from 1 to 2, so energy at section 1 is more as compared to 2. So we have E1 is greater than E2. So we have E1 is equal to E2 plus HF, and here E1 is nothing but P1 by rho g plus V1 square by twice g plus Z1. E2 equal to P2 by rho g plus V2 square by twice g plus Z2, and HF is the losses which are always positive. Losses can never be negative. Same concept we can apply for the pump and the turbine. Again, in this case the direction of fluid is from 1 to 2. In that case we have E1 is greater than E2. Depending upon the pump and turbine, we have to add the head of the pump or we have to subtract the head of the turbine. Suppose we have a pump given here, then the pump will give the system to the energy. So initially we have a sum here which is a low level energy E1, plus we give the energy to the system equal to HP. Whatever the total energy it will receive, it will attain the energy equal to E2. At the same time it will overcome the losses. Whereas in the case of turbine, which is normally driven from high altitude to the low, so this time E1 is greater than E2. So if we simply apply the law of conservation of energy, we have 2 in here and 1 out. So that is why we have 2 in is E1 HP and 1 out is E2. In the case of turbine, since the power is developed by the system to the surrounding, so this arrow is outward. So this time this is only in and these two are out. So we have E1 equal to the head developed by turbine plus E2. Whenever they ask you to find out the direction of flow, so simply compute E1 and compute E2. That is P1 by rho g plus V1 square by 2g plus Z1 and P2 by rho g plus V2 square by 2g plus Z2. Once you compute this, numerically check the value of E1 and the E2. If E1 is greater than E2, the direction of flow is from 1 to 2. In that case, we have, if you convert this inequality to equality, you have to write down HF on E2 side. And if we have E2 is greater than E1, then direction is from 2 to 1. In that case, since E2 is more, we have to write down HF on E1 side. We can apply the Bernoulli equation in the case of siphon. So we have a tube here and this one is called as siphon. We have shown the point 1 open to the atmosphere. Point 2 is just outside the siphon is 2. Point 1 and 2 you have to select such that they are open to the atmosphere, so pressure will be equal to 0. Secondly, assume that the tank is very large as compared to the size of the siphon. If you assume so, in that case the velocity V1 will be equal to 0. That is the ideal assumption here. So assume that A1 is very greater than A2. In that case we have discharge is A1 V1, A2 V2. But since here A1 is very large, so we have A2 by A1 is almost equal to 0. In that case we can force V1 equal to 0. That is the level in the tank is assumed to be constant. And finally, to find out the velocity at point 2, apply the Bernoulli equation between 1 and 2, neglecting the losses. If we apply this equation, we will get velocity equal to under root of 2 times g z1 minus z2. In this problem, they will ask you what is the pressure at point number 3. For this one, you can apply the Bernoulli between 1 and 3, or you can apply the Bernoulli between 3 and 2. So this time the velocity at point number 3 will be same as the exit velocity equal to v2. Apply this Bernoulli equation and we can calculate the pressure at 3. Since the level 1 is lower as compared to 3, it means that at point number 3 the pressure must be negative. So there must be a suction at point number 3. Then we have the application of Bernoulli, that is a flow measurement devices. The very first device is a venturi meter, second is orifice, nozzle meter, and the pitot tube. And again we have a small orifices. So venturi meter is basically consists of 3 parts. One is convergent, divergent, and throat part. Convergent part we have the pressure is going to change and dp by dx is negative. In the case of throat, the pressure is constant here, and in the case of the divergent part, the velocity is go on decreasing. So we have a adverse pressure gradient, that is dp by dx is positive. Whenever we have connected here U-tube manometer between the inlet and the throat section, then we always measure the piezometric head. And this piezometric head is given as P1 by rho g plus Z1 minus P2 by rho g plus Z2. If it is upright, in that case you have to use rho m by rho minus 1 equal to h, that is this position. That is, the manometric fluid is heavier than the fluid flowing through the pipe. You have to use this equation, and sometimes you have to use the inverted when the manometric fluid is lighter as compared to the working fluid rho. That time you have to take this value of capital H equal to hm into 1 minus rho m by rho. This discussion already we have done in the case of static. Now you can apply again the Bernoulli equation between 1 and 2 for ideal fluid and solve this step by step. In that case, we can calculate the velocity, that is the theoretical velocity, which is given as a1 upon under root of a1 square minus a2 square multiplied by under root of 2gh. To calculate the theoretical discharge, we have to multiply v2 with a2. So finally we have theoretical discharge is given as a1 into a2 upon under root of a1 square minus a2 square under root of 2gh. Coefficient of discharge is introduced here to calculate the actual discharge, and the CD is defined as Q actual upon Q theoretical. Value of CD is very high in the case of venturi, that is 0.95 to 0.98. So in that case we get the actual discharge is CD into A1 into A2 upon under root of A1 square minus A2 square multiplied by under root of 2gh. This h you have to remember when the manometer is given, you can calculate like this. Or you can remember the basic definition that h equal to P1 by rho g plus Z1 minus P2 by rho g plus Z2, because sometimes he will not give the manometer, rather than he can give you the pressure difference or pressure P1 and the pressure P2 as well as the difference between Z1 and Z2. Venturi meter is normally used to measure the discharge of a liquid. Orifice meter is normally preferred in the case of gases. So we have a simple diameter of a constant diameter duct here, and we have a orifice plate here. Orifice plate is nothing but a washer. A hole is made here. In this case, almost same equation is applied here, except the throat area you have to take the area of the orifice. So we have a Q actual equal to CD into A1 A0 upon under root of A1 square minus A0 square under root of 2gh. Calculation procedure for H is remains same, is hm into rho m by rho minus 1. Coefficient of discharge in this case, which is representing the loss of energy, is very low in the case of orifice. Clearly you can find here lot of vortices are produced. To rotate the fluid particle, that is the vortices, energy is taken from the system, and hence the value of CD is low. In the case of venturi, the orifice formation, the eddy formation are very less and CD is very high, that is up to 0.95. In the case of orifice, this value comes to 0.6 to 0.65. The modification of a orifice meter is the nozzle meter, where CD is improved because of less formation of eddy. CD is 0.7 to 0.9. If you are interested to know the local velocity, in that case you can use the 90-degree bend pipe, which one is also called as the pitot static tube. To measure the pressure, here we are using here piezometer. So we'll consider here two sections, section 1 and 2. Initially this tube is filled with water. Velocity equal to V1 at section 1. Water will enter here and water will rise here. Depending upon its energy, it will attain the maximum height equal to h2. Once this tube is filled, then the point number 2 will become a stagnation point, that the fluid velocity at point number 2 equal to 0. So this point number 2 is called as stagnation after some time, and V1 is called as the static point. So 1 is called as static, 2 is called as stagnation, and based on this height we can calculate what is the pressure at point number 1, which is rho g h1. At point number 2 we have pressure equal to rho g h2. Since these two sections are very close, we can apply the Bernoulli equation. At point number 2 velocity equal to 0, so we can very well calculate the stagnation pressure, which is equal to P2 plus P1 plus 1 by 2 rho v square. This term is same as the dynamic pressure. P1 is called as static pressure, P2 is called as stagnation pressure. And if we equate here the pressure P2, which is same as equal to P1 plus 1 by 2 rho v square. So P2 is the same as rho g h2, P1 equal to rho g h1, that is same equation I have written here, plus 1 by 2 rho v square. So rearranging this term, we can calculate here the velocity at the point number 1, which one is called as local velocity, is under root of 2 times g h2 minus h1. That is the difference between the stagnation head and the static head. So this arrangement is also shown you is a pitot tube, and we have connected here U-tube manometer. This time the value of h2 minus h1 you can calculate as a standard value of h, which is hm into rho m by rho minus 1, and here we can calculate the local velocity v1. If we are given the distribution of velocity, this time we have calculated the center velocity, and if we know the ratio of Vmax and V average, in that case we can calculate discharge using pi by 4 d square into U bar. But we must know the relation between U bar and Vmax. Some numericals are also appear on the case of small orifice here. So we have a very small size of orifice here at a distance equal to h. So h is the head above the orifice. Since the jet is living here horizontally, so initial velocity equal to v2. And to find out the velocity at point number 2, we'll consider point number 1, and one point is just outside this. So since here we assume the tank is very large as compared to the orifice, we have V1 equal to 0, P1 equal to 0, and Z1 is the potential head with respect to orifice equal to h. And now you can apply the Bernoulli equation, and you can calculate the velocity at point number 2, assuming that the tank size is very large, and you get the velocity equal to under root of 2gh. After this, they will ask you to what is the relation between x and y. So this problem is now shifted to mechanics, and we have a two-dimensional motion. One motion is along the x-axis and y-axis. For this one, you have to set the origin exactly where we have the orifice. Horizontal distance covered, which is called as range, is x, and the vertical distance is y. Since we have the horizontal distance is x and vertical distance is y, using the coordinate system and the two-dimensional component here, we have ux is same as uv2, and the vertical component is equal to 0. Acceleration along the x-axis is 0, acceleration along the y-axis is minus g. So apply the concept of displacement, which is equal to u into t plus 1 by 2 at square. Acceleration equal to 0 along the x direction, so this component will vanish, and we have x equal to ux multiplied by t. And we have ux is same as v2, so we have x distance will be equal to v2 multiplied by t. Now apply the same equation along the y direction and develop the equation for y, which is equal to 1 by 2 gt square. So we know the value of x and we know the value of y. So we know the value of x and y, we are able to calculate the velocity here. So just take the ratio and solve for v2. So indirectly this is an experiment to be conducted, and where the jet will fall on the ground, measure that distance and the height of the orifice from the ground level, that equal to y. Using this we can calculate here what is the exit velocity. The video you are watching is from the app, which is the More Class app available on Google Store, and in this app we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.